you're doing your continuing education credits for NABCEP, I'll tell you how to get those credits at the end of the talk by sending an email, and the email address will be at the screen at the very end. So welcome everybody. We'll go ahead and get started. So as I mentioned, we have an installer qualification program, and at the very end, I'm going to be highlighting this program. It's a way to get yourself on our map as an authorized battery installer with us, and we can direct some traffic your way. And as I mentioned, there's some benefits to this. Currently, we're running a $1,000 sign-up bonus, but it's only for a limited time. And there's a link to at the very end that I'll be sharing with you. This promotion was supposed to end at the end of last month, the end of March, but apparently we're going to be extending it for a short time to get some more installers in. If you are part of this program and you're installing our batteries, you can earn $25 back per battery installed as well. And there are other promotions that we have to help give back to our loyal installers, and we appreciate those of you that are installers on here. If you're not on here as an installer, no worries, we're going to jump right into the information. So Simplify batteries have been around for many years. We're probably the most tested battery in the market here in the US. We've been using cobalt-free chemistry since our inception over 13 years ago now. So we use lithium iron phosphate battery chemistry in all of our batteries. And that gives them a higher safety factor than other cobalt-based batteries such as NMC, etc. So essentially with LFP batteries, you have no risk of unmitigated thermal runaway. That means if a fire does happen, it doesn't go out of control with LFP as it can in other batteries in which the battery itself can be the source of fuel. So we have a high safety factor there using LFP. We're also certified with Underwriters Laboratory at 1642 at our cell level, 1973 at the battery module level, and then 9540 at the system level.
Hey, Nathan?
Yeah, go ahead, Daniel.
We had one question. We are asking, is it $1,000 just for signing up, or do they have to do something more than that?
Oh, that's great. So yeah, there are some rules around that program. It's $1,000 for signing up and then completing your first installation. So once your company is approved as an authorized installer and you complete an installation by the end of June, we will give $1,000 after you fill out a rebate. After you fill out the warranty for that installation. So there are a couple of steps and they're explained at the link, and I'll mention that again at the very end. So thank you, Daniel, for answering that, or for bringing that question up. Okay, so back to some of our certifications. We've done UL 9540A testing on all of our batteries, and we have UN Department of Transportation certification for shipping, and then we have special 38.3 certification to airship some of our batteries. That's with our ABS case. There are weight limits on air shipments. We are very well proven at this point. We've installed probably close to 100,000 batteries. We've had 100,000 batteries installed worldwide, over 300 plus megawatt hours installed in different countries, deployed in over 45 countries. We have a history of testing and validation with US Army and Marine Corps. So back in 2010 and 11, we did testing with them and demonstrated the safety of LFP battery chemistry. And we also have a business model that gives back by donating to various projects. We try to offer simple solutions for installers, systems that are ready to go and easy to install, and solutions that make sense. They're also highly scalable. We start with small building blocks in terms of our batteries so that you can easily customize and even add on to your existing systems. And these systems allow customers to maximize resilience, energy security, etc., giving customers a way to do time of use, peak shaving, demand charge management by adding batteries to solar installation. So I'm not going to go through this in detail, but we started as optimized energy storage back in 2010 and went through a whole product expansion line, lots of testing, development of intellectual property, advanced battery management systems, and really have refined our product over the years. And more recently in 2021, the end of 2021, Briggs & Stratton purchased Simplify Power. And so we are now under the umbrella of Briggs & Stratton Energy Solutions, releasing new products. Of course, Briggs has a history of generators, and so we are now having the ability to offer complete vertically integrated systems, such as our ESS system there, which can even include integration of generators. You may not know this, but if you have a large project, and if you're on here to learn more about large projects, we have a whole high voltage and large projects teams that can offer containerized solutions up to about the 1 to 2 megawatt scale. So as I mentioned, we've been deployed all over the world. We have a global footprint.
Nathan.
Yes.
Let's go back to that slide. We have a question. We do have a global footprint. We have a question. Do we ship to Cameroon?
I don't know exactly. I'm sure we have distributors that ship to Cameroon. So Simplify employs a distribution model, and we have over 30 distributors worldwide selling our products, and we definitely would have distributors that would ship to Cameroon. We have IQ installers in many different locations around the world. So I guess if you are curious about that and you want to know how to get batteries in Cameroon, give us a call. I'm going to provide our phone number at the very end, or you could get that phone number off the website, and our team will connect you with distributors that will supply in Cameroon. So great question. Sorry, I don't know the answer off the top of my head, but I'm sure some of our distributors do. I know that we ship products to various locations throughout the world, including Africa. Okay, so highlighting some of these products, I'm not going to go through a lot of detail on this. This training is more about teaching AC and DC coupling design considerations, but wanting you to be aware of the products that we do have. So we have products in these cabinets that you see. We call these our access cabinets. If we pair them with inverter pre-installed, pre-configured, and programmed to work with the batteries. We also just have a similar cabinet. It's got a temperature controlled fan regulation for airflow, and that can come with up to 12 batteries, giving you just under 46 kilowatt hours of storage in a NEMA 3R enclosure. We have mobile solutions, as you can see on the little Jenny pack that's there. High voltage stacks are shown on the right, and some of our various batteries at the bottom. The PHI battery, one of our most popular, Amplify battery with closed loop communications, and our newer outdoor rated wall mount battery, the larger 4.9 there at the bottom right side of this screen. So again, these are the batteries we're going to be talking about as we talk about AC and DC coupled systems. They come in fairly small building blocks at 3.8 on the smaller batteries. They are 4.9 on the bigger batteries, and then the cabinets, you can buy the cabinets to contain 6 or 12 batteries. And then, as I mentioned, the access cabinets can come with an inverter built in and pre-programmed. Okay, so what's driving the battery industry, and why are more and more people choosing to install batteries in their homes? People like Daniel and I work from home, or at least I work from home. And home as a haven, people are wanting to make sure that they have reliable access at home, both to the internet, because more and more of us are working online these days, and that desire for independence. We also have the challenge, right, that we have aging infrastructure in this country. California is well known for PG&E causing wildfires by having older equipment, older grid, which has caused a number of highly public fires in my state. There are climate-related disasters as well, so we're all aware that the climate-related disasters can cause disruptions to power, such as hurricanes, tornadoes, etc. And having battery backup allows people the opportunity to be able to keep the power on in their homes and keep working even when the grid goes down and when you lose access and connectivity. And then, of course, we can't forget that almost everything is electrifying. More and more people are buying battery-based cars, and so access to power generation equipment at home and power storage equipment at home is becoming more and more important. There is also the big need, right, to have clean energy and to be part of the solution, right? People want sustainable access to power. And so having solar panels is not enough if you want to have access to that clean energy in the nighttime. There's a statistic on the top right of your screen. Only 15% of solar owners have battery storage. And a survey has shown that about 61% want battery storage. Why don't they have it? Why aren't they installing it, right? Well, the upfront costs, right? There are high upfront costs for getting battery storage. Those are coming down slowly. And the reliability factor has gone way up with the introduction of LFP batteries. You get huge numbers of cycles out of LFP batteries. If you're discharging at only 80%, you're looking at something around 10,000 cycles, which can last a very large number of years compared to the typical 5-year lead acid battery bank. And so there are a lot of different end use applications for batteries. I'll highlight 3 of them in the next slide, but upgrading existing solar homes. So maybe somebody already has solar on their roof and they want to install batteries. They might have an AC coupled system, meaning they have microinverters on their PV panels, and they're just feeding back to the grid. Well, in places like California and other places around the world, the feedback and incentives for selling back to the grid are dropping. NEM 3.0 is starting just a couple of weeks in California. And so that means that power companies aren't wanting to pay large amounts. And so if you're not using the solar coming off your roof, what do you do with it? If you're not using it, you're not getting the money out of your investment. So one thing to do is to store it up over the daytime when it's being produced, and use it over the nighttime. Of course, there are incentives in place, and the new IRA gives more tax incentives for even just installing battery systems now. So you can look into that. As I mentioned, selling back power to the grid, it really depends on what the feedback tariffs or feedback rates are. But we also want solar ready new homes. And in California, new homes are going to be required to have solar panels in the future. Of course, if you're living off grid, getting connected to the grid can get very expensive. So there are many, many reasons to install battery. I'm going to highlight 3 of them here, talk about peak shaving. So it was just at the NABCEP conference with Daniel last week, and we heard from a number of installers about how peak demand charges, right? This is a charge based on what category, how much power you're drawing at one instant in time throughout the day. So the power companies are creative at how they charge you. And so if you end up having a demand that's very high when you start up maybe a piece of equipment, like an oven is starting up in a pizza shop, or a large machine is starting up in a machine shop, you can end up with very high power draws, but for just short periods of time. And the power companies can be charging peak demand rates based on that peak. If you have a battery system, right, and that battery system can supply some of that power and reduce those peak demand charges. Of course, there are time of use rates. So my electricity bill is based on a time of use where the power is much more expensive in the evening time, and the power companies charge more at the times when people are trying to use it. So by using batteries, you can smooth out the amount of energy that you're drawing from the grid. And of course, the last one, integrated solar plus storage, you can generate your power during the day and utilize it when you want to in the evening time or when you're at home. So as we get into the meat of this topic, AC and DC coupling battery banks, I'm going to start off with some basic definitions. All right, so how solar panels are coupled or connected to a battery bank is what is known as the coupling of the PV system. And so an AC coupled PV system is when you have an inverter typically tied, the array is tied directly to an inverter. And often this is in the form of micro inverters, but it doesn't need to be, right? You can have string inverters that are just directly sending that power to the grid. DC coupling is when you bring the DC output of solar panels into your inverter, right? And then your inverter can use that for charging. So typically the DC coupled strings will come into a charge controller, MPPT, or PWM with older systems. And then that inverter is responsible for converting that or inverting that DC power to create AC, which is used inside the home. AC coupled batteries. So there are all batteries, just like solar panels, are DC in nature. But an AC coupled battery is a battery that has DC cells inside it, but there's an inverter / converter that can convert AC coming in from maybe an AC coupled array into DC to charge the batteries. And then if you're coming out of the battery, it can invert that DC to bring it back to AC for usable export. So these are the basic principles that we're going to start off with, basic definitions. So let's start with DC coupling. Let's look at a DC coupled system. So as I mentioned, a DC coupled system, you're producing DC power at the PV level. That DC power from the generation source, as your PV array in this case in the picture, right, will then be used by a charge controller, and that charge controller will control the voltage and the current coming out of that array to charge your battery system. There's optimizations that are built into these systems to try to get as much power out of solar panels as possible. And we'll talk a little bit about those two different types, the MPPTs and the PWMs. And then there are also some considerations as you're looking at putting your PV in, right? If you have DC coupled PV panels in strings, there can be repercussions due to shading. So if one of the panels is shaded and those panels are in series, it can affect the other panels in that string. Most solar panels have some bypass diodes that are built into them to prevent having a complete disruption of power. But there still can be shading conditions in which, you know, one panel in the string can affect the other panels. With AC, there's a difference, and so we'll get to that. So there's some considerations in where you put those panels, whether you're doing ground mount solar, if there are lots of trees around and you will have shading issues, then it's important how you orient and where you put these panels, how high you put them, etc. And then there's some temperature considerations as well. Lower temperatures actually result in higher voltages on solar panels, and so I'll mention that just briefly. And of course, the amount of sunlight that's striking the surface of a panel will result in higher values of current through the strings. And you have to be careful not to get too much current through your strings because there are limitations there. So how does a panel work? I will talk just briefly about this. The way a solar panel works is there's two different types of silicon that are sandwiched together at the very top. There's what's called p-doped silicon and n-doped silicon below. And at the interface between those two is what's known as a p-n junction. There's something called a depletion layer where the n-doped silicon prefers electrons more than the p-doped. And so when sunlight comes in through that thin, transparent p-doped layer, it splits the electrons up, and the n-doped layer gets a buildup of electrons. That buildup of electrons, if you're not drawing them off of that solar cell, will result in a voltage. And if you're not drawing them off, that voltage will maximize out when the repulsion of the electrons from themselves balances out with the electric field inside the silicon. For silicon cells, that turns up at room temperature to be about 0.62 volts. That's the open circuit an individual solar cell would get. So just like batteries, to build up a large voltage on a battery, solar panels, solar modules end up having large numbers of solar cells, each of them contributing at about 0.62 volts. And if you string them together in series, that's how you get a higher voltage panel. So the solar modules are then joined into arrays. And that solar array is what we typically refer to as a string. So you take strings of those solar panels in series and bring them into the charge controller. What you're seeing on the bottom left is a typical what's called a PV diagram or a IV curve, where you're looking at the current on the vertical axis and the voltage on the right. So if we're not drawing any current out of the solar panel, right, then we'll end up at some open circuit voltage, which really just depends on how many cells overall are in series and what ultimately is the temperature, right? Because the temperature does have an effect. So lower temperatures, the open circuit voltage of the string will go up, and at higher temperatures, the open circuit voltage will go down. The job of the charge controller is to get as much power out of the panel as possible with more lighting conditions. So you get the most amount of light into the panel when the sunlight is striking from directly overhead. And the brighter the light is, the more amount of current that you'll get out of panels. So the job of the solar system is to provide this power, and the job of the charge controllers and the inverters is to kind of maximize this power. So they're trying to create current times voltage is power. So they're trying to create the biggest amount of area under this curve. And so that's often known as the maximum power point. So what does a charge controller do? A charge controller regulates the DC voltage and current going to the battery bank to hit specific set points, right? So we want to charge batteries at specific voltages and rates, and the charge controller is responsible for taking as much power out of the panels as possible in order to charge the batteries, and simultaneously, if there are loads on the inverter, to supply that excess power to the inverter to use for loads. If there's too much power from the solar array, the charge controller can do what's called clipping, and so just use the amount of power that it can direct either to battery charging or to loads or back to the grid. There are different sources, many different sources. Of course, most people are familiar with PV sources, and we focus on that because it's the most common, but there's also wind and micro hydro, and we do have plenty of people using our batteries with both of those applications as well. Two different types of charge controllers: MPPT, maximum power point tracking, and PWM, pulse width modulation. They essentially are doing similar things to control the output current from the array. MPPT detects solar panel output, that voltage, and in real time, it increases the load a little bit and decreases the load a little bit and sees how it lies on that PV curve and adjusts to get the maximum out of the solar panels. So it's constantly tracking in a type of feedback loop to maximize production. You can get up to 99% efficiency from these, although I think in real time there is a decent amount of heat generated, but typically numbers close to 100% are common. So 95 to 100% is not uncommon for a decent MPPT. They're much more efficient than the PWM controllers, but PWM controllers are much cheaper. And so in the past, historically, people would use PWM controllers. You can get a 15 amp PWM controller for about $15, so they are very cheap. And some of them have additional features built in. How does a PWM charge controller work? Well, it works by pulsing through micro switching. It works by pulsing the length of time that a voltage is available. And by decreasing the length of time that a pulse is coming through and averaging over time, you can reduce the amount of power output or increase the amount of power output. So they use FETs, field effect transistors, to do this, but they are less efficient in most conditions than MPPTs. They're a good fit for maybe some small systems. My colleague Daniel was telling me he has this SunSaber 20L that he's used for his ham radio. This has a built-in low voltage disconnect on it as well. I think he said it's limited to 20 amps. So that is an option, but most people are using something more like this. This is a newer Midnight charge controller. It's an MPPT. Some inverters, hybrid inverters, have the MPPT, the charge controller, built right into the inverter, and those inverters are capable of connecting with the grid, etc. This is a Midnight Classic. Sorry, Daniel, correct me. What's the name of this one?
That is a new one. That might be, they had come up with a new, let me look it up and I'll get back to you. While we have you here, Nathan, we had another question come in. Somebody's asking, how can we determine the number of solar cells on a module? Is it 60 or 72? And other than just counting the number of cells on a module, maybe could we talk about, well, what is the voltage of each cell, nominal, and then we could maybe infer what the number of cells are based on the voltage that we see on the nameplate.
Yeah, so that's a great question. So typically what we do if we're looking at a solar module is we'll count the number of cells across, in this case, 5 across here, and then we'll count the number of cells down, and I think I'm counting 8 here. So this is a 40 cell panel. The open circuit voltage of this panel at standard temperature, which is 25 Celsius, will be about 0.6 times that 40. So you're looking at about, somewhere around a 28 volt panel in open circuit, and then the operating conditions of this panel will further reduce it down so that the maximum power point will approximately be about 24 volts. So you can simply count the number of cells. These cells are strung together in series. So if you look at these these little nickel strips here are actually the wiring of the cell, and you can watch them go over and under each cell to produce that overall voltage. Some panels have more some cells that are wired in parallel in addition to series, but most panels are all in series. I have some 435 watt commercial panels at my house. Those have 128 cells and they operate at about 80 volts.
And it's called the Barcelona Midnight Solar, and Hawke's Bay is another one. That was, I believe, the one we're looking at there is either a 90 amp charge controller or 120 amp.
Okay. Yeah, and the amperage out of your charge controller is typically your limiting factor. So if you have a 24 volt system, you're getting half the power that you can from a 48 volt system. And so we'll talk about that a little bit. We have 24 volt options for batteries, but most people are going to 48 volt. We were just talking to Midnight Solar last week at NABCEP and looking to get communications between our batteries established with Midnight Solar. So stay tuned in the future for that. So how does an MPPT charge controller work? MPPT charge controller work? As I mentioned before, the amount of power you're getting, if we're looking at a current versus voltage diagram, depends on the amount of area that you get under the curve. And so if we're way down here at low voltage and we have full current, that's what's known as short circuit current, you're getting no power. And so that's why the blue power curve here is starting at 0. So as we increase the amount of current, the voltage stays fairly constant for a while until we start pulling off electrons faster than they can be generated by the PN junctions. And then the voltage starts to drop off. So you see almost a linear increase in power until we get to this point where it maximizes, because as the voltage is going up, the current starts coming down. And so this is the maximum power point. And what this charge controller does is it adjusts the amount of current it's pulling off of the solar array. It makes the current, it increases the current a little bit, sees what happens to the voltage, computes the power, decreases a little bit, sees what happens to the voltage, computes the power, and it keeps moving that maximum power point around depending on the conditions. So as the array gets colder, that red IV curve changes, right? And the VOC goes up. As more sunlight is available, maybe the sun is changing the angle in the sky, more current's available. And so the MPPT charge controller is constantly trying to optimize the amount of power it's getting out of the array. So a DC coupled system, here's an example of a DC coupled system. We have a charge controller. It looks like a 75 amp Victron MPPT charge controller there. And that's landing on a bus. That bus is connecting the batteries to the charge controller, but it's also connecting the inverter, right? And so the job of the charge controller there is to bring current in from the solar array, maximize the amount of power it can bring in, distribute that to the batteries if they're in a charge cycle, and if not, allow that current that's being produced to run through the inverter and either feed loads, the light bulb, or send it back out to the grid, that grid symbol that's there. So what lands on the DC bus? The inverter, the charge controller, and the batteries. And then, as I mentioned, I mean, this is an example where you have a separate charge controller and a separate inverter, but you can have the case where the inverter and the charge controller are one. And in that case, the hybrid inverter would directly land on the bus. and then the solar array would come into that hybrid inverter. So here's an example of a DC coupled system. What you see on the upper left is solar panels. Those are Tigo rapid shutdown devices. So rapid shutdown devices are there so that a button can be pushed to turn off the power output from that solar array in the event of a fire or some type of emergency. And so those Tigo controllers are basically switches that are electronically controlled interrupts, and those interrupts run through a signal in the PV cabling. And so the transmitter is that green symbol that's there. That's a Tigo transmitter, and then we've got a Solarc inverter here. I think that's a 12K, and then we've got a midnight combiner there, 2 battery banks. These are 2 of our Boss 12s, so it's a huge amount of storage that's there. It looks like 95, 94-ish kilowatt hours of storage. That's a very large backup system. And then that Solarc is coupled to a critical loads panel, as well as to the grid for export. So the typical example of a DC system, the only thing atypical about it, I guess, is the large number of batteries there for backup. So with AC coupling, things are a little bit different. One issue with AC coupling is that, and first, just to explain what AC coupling is, you have solar panels on your roof, and typically micro inverters or inverters that are taking that power from those solar panels, which makes DC, and immediately converting it to AC. The difference here is that you don't have DC to be regulated to send directly to the batteries. So you've got AC coming from your array. And if you want to add batteries to this type of a system, you need to turn that AC back into DC. So it's essentially the solar array is going directly to AC, and then you're going to use that AC to couple to batteries. And in order to do that, you have to have another inverter converter to convert that back into DC to charge the batteries. The big difference here, of course, is that you'll need that second inverter. Why might you want to do this? So AC coupling of batteries to AC arrays is very useful when those arrays are already on the roof. So you don't want to go back up, completely rewire a new solar array. You don't want to have to get up on the roof. So you can just buy an extra inverter, keep the existing AC solar array, and still add batteries to it. So frequency shifting is a mechanism that's used from battery-based inverters to regulate or control grid-tied inverters output. So if you've got that AC system on the roof, those micro inverters are up there trying to produce as much power as possible. Let's suppose we're in a grid down situation in which the grid is not producing power. If you don't have batteries and you don't have any kind of backup, most people don't know this, or a lot of people don't know that AC coupled solar arrays cannot produce if the grid is down and you don't have battery backup. So it's a downside to having an AC coupled solar array, is that if the grid's not there, you don't have any backup. Well, the way you can change that is you gotta add batteries. You can add AC coupled batteries by bringing in an inverter, which can charge the batteries. But in a grid down situation, that inverter will produce AC signal. It can keep alive that solar array that's on the roof by producing a pure enough signal. As micro inverters see that there's that signal there, they start producing power, but that power has to go somewhere. All right, so the micro inverters that are producing AC on the roof, you need a way to regulate their output. And the way that's done is by frequency shifting. So the controlling inverter for the batteries that's forming the grid can shift the frequency upwards above 60 hertz, maybe go up to about 62, 63, and that can send a signal to the micro inverters to output less power, get some clipping out of the micro inverters. So this is called frequency shifting, and it's needed by the inverter coupling the batteries.
Nathan, we had another great question.
Sure.
when you DC couple, is it more efficient than when we AC couple something?
That's a great question, and it depends, right? So overall, yes, because if you think about every time you're converting energy from one form into another, you generate some heat, and heat is waste energy, right? And so if you're only converting once, and using the DC from your solar array and going directly into a charger, you're going to have a more efficient system. However, one of the nice things about AC coupled solar arrays is that one panel doesn't mess up a whole string. Since all of the microinverters are producing AC on the roof, right, you don't have as large of a consideration with shading, knocking out strings. Now we'll talk about DC optimizers in a second. And as I mentioned before, most modern panels have bypass diodes that are built into them. But there are a number of considerations that goes into how much energy is coming off that solar array. So from a physics standpoint, yes, DC coupled is more efficient. From an energy production standpoint, it depends on other things such as shading. And one of the arguments the micro inverter companies like Enphase make is that they don't have as much of a problem with shading issues. But I'm on the DC camp here. I think that in general, not only theoretically, but a well-designed system that's DC coupled is better. However, if you've already got an AC coupled array on the roof, I would by no means tear it off. I would use it and just AC couple a battery bank if you want that battery backup so that you can have power coming from your solar array or just from your batteries during a grid outage scenario. So here's a simple example. This is just a grid tied. I hope I answered that question. Daniel, did you want to add anything?
No, that was great. Thank you.
This is an example of a grid tied PV. So we've got solar panels there, and those are Enphase IQ7 pluses, microinverters, feeding into a combiner, and then sending that AC signal out of the microinverters out to the grid. So it's a grid tied PV array, AC coupled, or sorry, grid tied array. Here's an example of an AC coupled system. So the coupling refers to the fact that we've got AC coming out of the solar panels because of these microinverters. They're still running through a combiner. And so the solar is AC coupled to the battery system. And so to turn that solar back into DC, we need an inverter / converter. And in this case, it looks like a solar that's there in one of our access cabinets. We've got 6 3.8 kilowatt hour batteries there, giving you about 23 kilowatt hours of backup storage. And then this is fed out to the grid. And one of the nice things about this system compared to the previous system, if the grid goes down, you've got no power coming off your solar, right? There's no backup for an AC coupled solar array, right? You need batteries for that, because if the grid goes down, the microinverters turn off, right? Now, if we have a battery system, this solar can be grid forming. It can produce an AC signal that the microinverters can latch onto, and you have power coming from your solar array even when the grid is down. And because of the batteries, even if it's dark, you can still have battery backup even when the solar array is not producing.
We had a question, Nathan, if you could go back one slide. Somebody is asking about a practical case study in which one way is better, AC coupled or DC coupled. And I think this is a great example of when an AC coupled system is a better case study, because it allows you to retrofit, come out to an existing site and not get up on the roof or change anything on the array. Don't even have to get the ladder off the truck. And
don't have to get that additional permit. Right.
That's right. And we can go ahead and AC couple on. I think a case study for a DC coupled system would be a new install, when we can get up there and avoid some inversion losses and use optimizers to
deal with shading.
Yeah,
it's a great example, Daniel. If you've already got an AC array on the roof and if you've never installed battery backup to an AC system, it's a perfect opportunity where the best scenario, as Daniel mentioned, is to come in and AC couple your battery bank. Even if it's just a small battery bank, then as long as that solar is out there, you would get power during the grid outage, right?
Yep. Yep, exactly. One great point about this Solarc and our new inverter that we have is that they're both able to be AC coupled or DC coupled. That Solarc has built-in charge controllers. So they're called hybrid inverters, and it allows you to do both all in one package.
Thanks. Let's talk a little bit about applications. Obviously, in off-grid, you're most likely going to be DC coupling, right? There's no grid there for you to latch onto with a microinverter. So almost always you're looking at a DC coupled system. When you're off-grid, you want to understand float charging. And so we want to keep our batteries safe when we are off-grid, which means typically we don't float our batteries. And if we do float them because we have free renewable energy and if we're not doing anything with it, you know, we're not collecting any power if we're not sending it somewhere. So one of the things you can do is float our batteries at 54 volts. That'll keep those batteries topped off at near 100%. But you want to make sure that you understand that float is not as often used at lithium batteries because the self-discharge rate of lithium batteries is typically around 1% per month. So unlike you know, a lead acid battery, if you leave your car sitting for a month, you know that there's a lot less energy stored in that battery. It self-discharges much faster. Lithium batteries, you don't have that problem as much, and so typically we're not floating unless that energy is kind of coming in for free. And then we don't want to float at high voltages because long-term exposure at high voltages for lithium batteries can cause damage. For battery backup, you can have grid down situations and islanding mode. And so we want to make sure that our devices are able to anti-island in the case where a grid goes down, because those batteries that are there allow the inverter to keep producing solar. And we don't want to be feeding that back to grid. Daniel, what's the name of those? Is it MIDI? What's the device that prevents that inside inverters? Typically,
let me get that exact name.
Okay. Grid tied features offer us the ability to sell back to the grid as well, time of use, and allow us to do things like peak load shaving. So if you're drawing a large amount off the grid, if you have a CT, a charge transformer that is recording the amount that you're pulling from the grid, the inverter and your batteries can supply some of that load to reduce that overall current that you're drawing from the grid. And so that allows you to reduce the peak demand charges.
A microgrid interconnect device, it essentially functions the same way as a transfer switch would. Automatic transfer switch.
Thank you, Daniel. I was asking Daniel about that right before this training. So AC coupling, again, as Daniel said, an excellent scenario is maybe you have an AC coupled system already existing on a roof. You want to add battery backup. You want to have that power available when the grid goes down. And the most likely way you would do that is by coming in and AC coupling a battery bank to that existing array. Grid down situation, you've got battery backup. Well, those solar panels from the AC coupled system are not going to turn off now because you've got a grid forming inverter that can keep those microinverters alive. Use case limitations, time of use. You have time of use considerations here, self-consumption. You want to use that power, or peak shaving. These are all opportunities to use that AC coupled system with a battery bank to save your customers money and to give them some power independence. So here's an example with an existing, looks like AC coupled array, and this Fronius inverter is being used to convert that AC, to couple that AC signal from the solar array to charge a DC battery bank. Misconceptions about DC coupled grid tied systems. Sometimes, so I'm not sure exactly what is meant by this slide here, derived from retrofit challenges. So there are challenges to putting a DC system in that arise from retrofit. And if you already have an AC coupled system on the roof, and you don't have those problems with shading issues, then the misconception is that the DC coupled systems have much larger problems with shading issues. I think that that's not necessarily the case, and we'll get into DC optimizers a little bit, and that's what the next bullet point there is on the efficiency of PV, AC versus DC coupled. So optimizers allow you to deal with some of those shading issues, and then grid tied inverters, don't have battery backup that's built in. And so in some circumstances, those might be more efficient. Rapid shutdown devices. So for DC coupled and AC coupled systems, you have to have something to turn the solar array off in the event where a grid system goes down. So for a DC coupled system, we showed a TIGO example earlier. Daniel, what's the other common one that's being used?
AP Smart.
Yeah, go ahead.
Yes, you had it.
AP systems, yeah. So AP or TIGO are common ones that are out there. And so these are rapid shutdown devices that basically, in the event of an emergency, you can push a button and that will shut down the solar array's production of power. So you don't have high currents and power production when you need to shut it off. And these are required in most jurisdictions. You need something to shut off that solar array. And so the TIGO and the AP Smart, those are rapid shutdown devices that send a signal up to the interrupts, which are at the location of the solar panels to turn off that solar array. In AC coupled systems, you also want to be able to shut off that 240 volts that's coming from the solar panels, right? You want to be able to shut that off. And so one way to do that is these microinverters have built-in shutdowns. If they don't see a grid, or if they don't see a 60 hertz signal, right, they will shut off, and that's a compliance issue, right? If you add a battery backup, right, then the inverter is keeping that solar array alive, and in order to shut it off, right, you have to be able to have a shut off button, which will quickly shut down the inverter, which is the grid forming inverter. And then once the grid is shut off at the inverter coupling the battery bank, then the solar array would shut down too, because it wouldn't see a nice 60 hertz sine signal. So here's an example of a DC coupled with a shutdown device. So this red button that you see on the screen, that is a shutdown button that will turn off the signal, the keep alive signal coming from the transmitter. That will cause an interrupt inside these rapid shutdown devices, which basically just opens a switch, opens a contactor, and prevents the solar array from outputting current coming into the system. So this is a rapid shutdown button. Here's an example in which we have an AC coupled example. Here's a disconnect switch to turn off. We've got 240 volts coming from the microinverters coming through this disconnect, and then that's coming through a combiner box and going into, this is looks like a Schneider 6848, I think this is. And so the Schneider is responsible for shutting down these inverters, and we need a shutdown button to do that. So some simple design considerations. So for DC coupled systems, you're typically limited by the amperage of your charge controller. So common amperage limits on charge controllers are something like 80 amps or 100 amps per charge controller. And so sometimes you'll use multiple charge controllers to be able to bring in the full amount of power from a solar array into a battery bank. Typically, your strings are limited in the number of panels that you can have, because as you stack those panels in a string, the voltages add up. And so typical voltages on charge controllers can be anywhere from 100 volts for a small MPPT all the way up to around 600 volts. Our inverter, our hybrid inverter, has 600 volt limit on the strings. Wiring runs, so you lose power in wires. So there is a little bit of electrical resistance in copper wires. That depends on the gauge of wire you're using. people very frequently use just 10 gauge wire to connect their solar arrays, but if you have a very long wire run, you can lose significant voltage along that wire run. I'll give you a good example of that. I installed a sun pumps water pump over 1,000 feet distance. The wires were running from the solar array over 1,000 feet distance to get to a pump, and at 60 volts coming off of our controller, we were down around 48 volts by the time we got to that pump. And yes, you can use larger wires to reduce that, but larger wires are expensive. And so long wiring runs can reduce voltage or reduce voltage proportional to the current as you go along the wire runs. So typically that also can get expensive. Higher voltages mean less current, less loss, less expense on the wires, but you're limited there in terms of your MPPTs. The nice thing about having a DC coupled system is also having the critical loads panel and being able to do backup of only certain loads within the house. AC coupled systems, you're limited in amps through the inverter's internal charger. So basically, you put in a charger that will be able to charge your batteries, and you're limited to the amperage that inverter can output at the voltage of your battery bank. You have grid down limitations and sizing concerns versus grid up. So when the grid is down, we have to be very careful, because when the grid is down, then the inverter will be sending all of the power coming off that solar array to either the loads or a charging cycle. And you have to make sure that inverter is capable of frequency shifting to turn off the microinverters so that you're not overcharging a battery bank with an AC coupled system. So you always want to size your battery bank for an AC coupled system based on the output of the inverter. So if you have a 6,000 watt output inverter, you want to make sure that your battery bank is capable of charging at 6,000 watts. Okay, nicer thing is there's a little bit less wiring for AC coupled systems, and basically everything is coming in at 240, and there's less wiring to do to get things set up. For some of our products, I'm going to highlight some of our features. So as I mentioned before, all of our batteries use a lithium and iron phosphate chemistry. It's a safer chemistry, less toxic chemistry, doesn't have cobalt in it. We also use cylindrical cells, which are the most expensive cells, but they're also the longest lasting and give you the best amount of performance out of them. Some of our competitors use prismatic cells, others use NMC cylindrical cells. So we're really using the best of both worlds, especially for home storage. So LFP batteries are a little bit heavier, but they're longer lived. You get great depths of discharge. You don't have problems keeping them 100% charged. So really long lives out of them. But they do come at a slightly higher price point, right? So you're paying for that quality that you get with ours.
Nathan, so that was actually one of the questions in the chat was,
sure.
What is the cost of an LFP per kilowatt hour? And I think the math would be easy for you just to go online and see the price of a battery and divide that by the number of watt hours or kilowatt hours per battery. And why is it important? And you mentioned a few things. Why is it important to look just beyond the upfront price of a battery and look at the lifetime cost of a battery?
Okay, so that's a great question. And I also want to say, not all FP batteries are equal, right? There's a huge amount of differences in the construction, and I do a talk on the chemistry and how these batteries are made, et cetera, but the thickness of the batteries, of the cathode and anode inside the battery cells, the type of construction, the quality of the purity of the materials, the consistency of the cells is one difference, right? But you can have LFP pouch cells, right? You can have LFP prismatic cells. So LFP alone doesn't mean you're getting the best battery possible, right? There's different levels of quality of the cells. So we're using premium cells in our batteries. One of the downsides of pouch cells, right, is that the pouch cells can easily be punctured, and they experience, as they heat up and contract due to internal resistance. It's a natural thing for all batteries to have some internal resistance. The pouch cells end up swelling and then contracting, and those changes in shape, the repeated changes in shape, can cause less lifetime for pouch cells. So the cheapest cell you can get is a pouch cell, but you're not going to get as many cycles out of it. And the same with prismatic cells. They can be decent. They're a little bit lower cost, and because they struggle with getting rid of heat as well as cylindrical cells, because prismatic cells are not as good at getting rid of heat, they don't last quite as long. And that's the reason we use cylindrical. But even all of those things being considered, even if you built the whole system with the exact same cells, you also have the battery management system, and we've developed and refined our battery management system and the way that we use those cells to be able to deliver a really long lasting battery. So there are a lot of things that go into making a good battery. LFP chemistry, I think, if you're doing a home system, is the best type to use. Cylindrical cells, you know, you could save some money by going with prismatic cells. And then, to answer the question, then the cost per kilowatt hour goes down a little bit. But then you get a slightly lower lifetime, right? So it depends on what you're after, right? If you're after a system that you only want to get, 8 years out of, and you're really just looking for backup, maybe a prismatic option would be the best option for you. If you're looking at a system you're going to cycle daily, get your money out of your battery by storing that energy, using that energy, storing it, using it. If you're going to cycle that battery daily, I would highly encourage you to go with cylindrical cells with kind of a top of the line BMS, which are the kind of batteries that we make. So many things to consider, and I guess to give you a rough idea is if you're looking at a kind of a premium battery, you're looking at about $700–800 per kilowatt hour. If you're looking at cheaper prismatic batteries, you're looking at maybe $500 per kilowatt hour. And if you're looking at pouch cells, you can get down to maybe $200, but you're not going to get much lifetime out of them. So we use something called the levelized cost of energy, which factors in the number of cycles you'll get out of the cell, the depth of the discharge, the change in the capacity of the cell over time to estimate kind of what the best option is for a customer. And in some cases that might be prismatic, in some cases it might be cylindrical. For home battery backup, I would never use pouch. It's just too dangerous. Okay, so we have safety testing that I've mentioned. We have 1642 at our cells, 1973, and then 9540 at our system level. We have that with Schneider, Solarc, and I'm not sure if we're quite done with that with our own inverter. And hopefully we can expand to other companies as well. UL certifications are often needed to meet local building codes and fire codes. We're one of the few battery companies, I think there's only 3 of us that are approved by the Fire Department of New York to install battery storage in New York City. And so AHJ's, local housing authorities, also can require these UL certifications. So if you're installing a system and you want to be in compliance with local regulations and meet building code, make sure you look out for solutions that have UL listing.
And Nathan, back one slide. We had well, we got 2 questions. I'll go. The first one is somebody had asked, are you planning to make cabinets with a 1-hour fire rating? I'm not sure exactly what you mean by that question. I will say this, that part of our UL 9540A test protocol, we sent our batteries inside of a battery cabinet to the UL labs, and then they go through a full-scale fire testing. And that's when we were able to achieve the requirements for spacing for maximum amount of battery capacity in one location that were called out in our 9540. So our battery cabinets, in a way, are tested for fire protection under this 9540A test protocol. There isn't really a specific fire rating per the batteries. And if I got that answer wrong, please retype your question there.
And feel free to reach out to us too. If we don't know the answer, we can get it for you. But I think Daniel's pretty familiar with this test. And one thing that I'll say about our company is that we're quite proud of our safety ratings in our test. And we publish the video of these battery tests. And so you can find that by looking on our website. And if you're interested in seeing more about that, we can share that with you. We publish it. And we would encourage other companies to do the same.
And one last question,
Sure.
or maybe not the last, but another one. Is there any difference in the expected life expectancy or cycle life between 24 and 48 volt batteries?
Well, that's a great question. I think the answer is really it depends on how you're using the batteries and how much power you're drawing out of them. So it really depends on how you're using the batteries. I think that inherently no, but our battery surge limitations, if you're surging your batteries often, our 24 volt batteries have a lower power surge rating. And so to some extent, they're a little more protected that way. But if you size your system appropriately, it's the same premium cells. We use the same premium cells in our 24 volt batteries versus our 48 volt batteries. It's just that the 24 volt batteries have more cells in parallel, twice as many cells in parallel, and then only 8 sets in series instead of 16 to get to that 24 volts instead of 48. So inherently, no, there's not a major difference, because from a cell perspective, they're seeing the same thing. But in terms of surge, I'll get to that on the next slide, actually. So let me come back to that. So we have some small format batteries. Typically, people use these for mobile applications. Maybe you want to have that power when you go camping. And so people will use these types of batteries for that. But we were talking about AC coupling home systems and DC coupling home systems. And more commonly, this PHI battery is used. So this PHI battery comes in 24 versus 48 volt sizes, and it's capable of surging at 80 amps. Now that's the 80 amps for either the 24 or the 48, and that's what I was trying to point out, is that when you're surging at 80 amps for a battery that has a total capacity of 151 amp hours, it's not as big of a deal, right? And so that amperage limitation really has to do with the size of the breaker. So all of our batteries and BMS units are limited to limited by that breaker and by the BMS. And the next battery that I'll show you, so this is the PHI battery. I'll show you another example. This is the Amplify battery. This battery has multiple internal temperature monitors. It has temperature monitors on the BMS, and it can detect the cell pack temperature at multiple locations, has an advanced BMS in it with closed loop communications. This battery is capable of surging at 100 amps for up to 10 minutes. And even larger amperages for shorter periods of time. It has that closed loop communications that's built in. You can parallel a very large number of these batteries up to 72. This limitation is really based on the communications cabling. Typically though, if you're going to parallel that many batteries have that huge of a storage, 275 kilowatt hours, people look at high voltage racks then, and we have a whole containerized solution that could be more economical than doing that many batteries. But we have had people parallel, I think about 40 of these to power larger systems, and the closed loop communications work there. This is a 5 kilowatt hour wall mountable outdoor rated battery. There's a conduit box that'll cover those top battery terminals that are there for your connections. This hangs on the wall just like a picture frame. I think it's about 6 inches deep. 4.9 kilowatt hour blocks. You can parallel these. These also have closed loop communications, also have the ability to surge at 100 amps for 10 minutes. The batteries with closed loop communications only come in the 48 volt kind of home standard now. And then our battery cabinets, we have the Boss 6 cabinet, which can hold up to 6 batteries, up to 23 kilowatt hours, outdoor rated NEMA 3R, temperature controlled fan built in. The bus bars are built in for you, and it makes it, the battery buses are built in, and it makes for an easy setup and connection, as well as a nice clean look, and you can install it outdoors. Same with the Boss 12, although larger capacity, higher power output capacity as well. And then the access cabinets, they can come in as little as 3 batteries and up to 6 batteries with the Solarx. And you can, of course, pair the access cabinet with a Boss cabinet if you want even more battery backup. So some things to keep in mind, that when you are AC coupling, because you are limited in terms of the charge controller, you're limited with a number of batteries, you're limited to a certain size power output, right? So if the array is producing 5.7 kilowatts of power, then that power would all be going into the batteries in a charging cycle if loads were not drawing some of that power away. So we never size our battery bank. We always size our battery bank to the output of that solar array, or vice versa, right? If you already have that solar array, you're going to choose the number of batteries. Each battery is capable of 1.9 kilowatts of charging. So if you have a 10 kilowatt solar array, divide by 1.9, and that would be the number of batteries that you need. Round up to the nearest whole number, of course. And so these are some limitations you want to consider. I've got some sizing tools that are here. It can help you size a battery bank. Maybe you've already got that AC coupled array on the roof. You want to add a battery bank that works with it. You can use these sizing tools to help. If you're doing a lead acid replacement, you can use these sizing tools to help. I'll be sending everybody a copy of this presentation after it's finished in just a minute here. Wanted to highlight, again, I mentioned at the beginning of the call, if you're an installer, installation company, you're installing our batteries, sign up. This installer bonus will give you $1,000 back after you warranty your first system. So sign up for our IQ program, install a battery system, and get a $1,000 check in the mail from us once you register that warranty. So that's all there is to that. We never get to offer this big of a bonus. So Daniel and I are pretty excited to be able to offer that back to the installers that have been attending our trainings. So additionally, when you do sign up for this program, it puts you on our map, lets us direct traffic to you. We get customers that call in and say, hey, can you recommend an installer in my area? If you're on our map, you're the first company to be recommended. And so if you join our program, you get $25 back per battery installed as well. So the only thing you need to do to get that check is to just register those warranties, and we'll process it and send you a check. So if you install a 10 battery system, you get a $250 check from that. And as well, right now, if you sign up and you're a new IQ installer, you're eligible for a $1,000 bonus. If you have questions about systems, so we can try to answer some of them right now, but if you have additional questions, you feel free to call our tech support or our pre-sales, where you have application engineers that can help you design a system. And if you have a high voltage questions, call in as well, and we can direct you to the high voltage team. So I want to thank you for your time. I appreciate you going through this training with me. Hopefully you learned some things. If you have additional questions that don't get answered, email us training@simplifypower.com. One more thing, if you're here for NABCEP credits, email your name as you want it to appear on your certificate. We'll generate those certificates and email them back to you. So email your name to training@simplifypower.com. Thank you. Daniel, are there any questions?
No, we were able to answer a lot of them during the training. We're getting a couple thank yous in there. If there is any last minute questions, go ahead and pop them in right now. And with that, I would like to thank you, Nathan.
Thanks, Daniel, for being on here, and thank you everybody for attending the training. Take a chance to sign up for this bonus while it's there. It's going to be ending soon. So I'll send a copy of the slides out to everybody. So thank you so much for your time. Goodbye.